Okay, this is a second example for virtual work. Oops. And in this example, we have two links that are connected together with pin connection, so smooth pin connections, so no friction. And you see that when we pull on the force P, the two links are moving to the right and up. Okay, so there's just 1 degree of freedom because they are moving together. So it will go like this. It's really exaggerated, but that's the way it's going. And the question is for theta, it's equal to 60 degrees, and the mass of each link is 20 kilo. Okay, so because delta U it's equal to F times delta R, I will do on the left the free body diagram with the forces, and on the right the displacement diagram. Okay, so on the left I have the weight on both link, put it a bit bigger. So in the middle at G, okay, let's call that G1 and G2. Oops. And for the forces at A, it's a pin connection. So I have AX and AY. At P, there's a force P and a normal force NC from the surface. At B, there's no force because it's internal. Okay, so the force of the link AB on the link BC and the link BC on the link AB, it's are internal forces and they cancel each other. Okay, so now for the displacement on the right, A. There's no displacement at A because A is a pin connection. So I will use the point A as reference. So that will be my axis X and my axis Y. Okay, because the point A never moves. At C, we have a displacement in these directions, delta axis. So what we need to write the coordinate of C, the axis of C. So for that, we have the angle theta and we have 1.5. So the axis C is equal to 2 times 1.5. And this is the projection cosine theta. So axis C is equal to 3 cosine theta. And let's find right away delta axis C. It's equal to the derivation of cosine theta is minus sine theta. So minus 3 sine theta delta theta. We need also to find the displacement of the point G. And just on the Y, because you see the W, the force W, is vertical. So we just need to find the delta YG1, and it will be also equal to the delta YG2. Okay. So let's find YG1, and it's also equal to YG2. So this is these dimensions. So this is equal to minus 1.5 divided by 2. And this is the, so this is this distance too. This is the sine of theta. And then delta YG1, it's also equal to delta YG2. And it's equal to minus 1.5 divided by 2 cosine theta delta theta, the derivation of sine theta. Awesome. So now let's write our principle of work and energy. We have the force P times the delta axis plus the force, the W, let's call that the W1, times the delta YG1 plus the W2 times the delta YG2. It's equal to 0. I didn't include the sign yet. That's just the general formula. Okay. Time and time. Okay. So now we need to include all the sign for the forces, all the sign for the delta. Okay. So P is going to the right, so it's positive. So P times delta axis, it's minus 3 sine theta delta theta, not this one. Why is it negative? It should be positive because it's going in the same directions. Let me think 10 seconds. Yeah, the overall displacement for sure is positive. Let me look at the other one with W. So W1 is going negative, so minus W1, and delta YG is equal to the minus 1.5 divided by 2 cosine theta delta theta. Oh, that will be correct because this one will be positive and this one will be negative. And for the W2, so that W2 is going down, so minus W2, and the delta YG2 is also minus 1.5 divided by 2 cosine theta delta theta. And everything is equal to 0. Okay, so there's something that's a bit weird there, but the product p times minus 3, it will be negative, and this one the product will be positive, and this one the product will be positive. What is important is that they are in opposite direction because P and delta C are going the same directions, but W and YG and YG2, YG1 and YG2 are going in the opposite direction. So for sure, this one must be in the opposite sign of this one, and this one should be in the opposite sign of this one. That's a bit a mystery sometimes with the virtual work for that. Try to think one more time, but I think that's what it is. Yeah, and you see if it will have link on the top, we will have the exact same W. Oh no, and the weight will be in the same directions. So anyway, let's keep going with that. So we can remove all the delta theta. Okay. So we have minus 3 P sine theta. Let's switch color. That's cool. Plus 1.5 divided by 2 W1. So W1 is equal to 20 times 9.81 cosine theta. We can write 2 times this plus 1.5 divided by 2 times 20 times 9.81 cosine theta. It's equal to 0. So let's write that P is equal to, so 2 times this, so 1.5 times 20 times 9.81 times cosine 60 degrees divided by 3 times sine 60 degrees. How much is that? 1.5 times 20 times 9.81 times cosine 60 and divided by 3 times sine 60. This is equal to 56.6 Newton. So to keep the equilibrium of those two links, we need to apply a force of 56.6 Newton at P, and it will balance the work done by the weight of the two links in this position only. So that's it. Sorry for the mystery with the sign. I will think about it. Bye-bye.